Welcome to another video where we are going to answer some questions for physiology. First question is, the first thing it's asking is to describe the composition of blood. So blood is over here. It is made up of RBCs, plasma, and it also has this buffy layer, which is where your white blood cells are located. And in the plasma, it is going to be made up of albumin, globulin, and fibrinogen. And if it doesn't have fibrinogen, it's going to be called serum. We'll come back to this stuff over here. All right. Next, it says describe the mechanism by which red blood cells are removed from circulation. So red blood cells are going to be eaten by macrophages in the liver, in the bone marrow, and in the spleen. Let me just type in bone marrow for you there. And then its organelles are going to get recycled. And then the hemoglobin is going to be broken up into heme and globin, in which the globin is going to be made up into, is going to be broken down to the amino acids, which are then going to be recycled. So that's how the red blood cells break apart. How they're made is through erythropoiesis through bone marrow, and erythropoiesis is also known as EPO. And so, yeah, and then it didn't ask about hematocrit, but I did like to talk about it just because I work at a plasma center. So hematocrit increases whenever you increase in elevation or dehydration, and then it decreases whenever you're hydrated, because hematocrit is your RBC level percentage to your plasma, compared to your plasma. All right, now we're going to discuss how heme is broken down and what happens to the various components. So heme is going to be made into biliverdin. Biliverdin is then going to be made into bilirubin through different oxygenases. And then the bilirubin is going to make its way by being carried by albumin all the way to the liver. And then the liver is going to take this nonpolar biliverdin, and it is going to attach glucuronic acid, which is going to make conjugated bilirubin. Whenever it's conjugated, it's going to allow it to then go into the intestines. Once it's in the intestines, the bacteria in them will emulsify the fat, taking off the glucuronic acid, turning it into urobilinogen. And that, because it's nonpolar, it can then go through the walls back into the bloodstream, or it can be secreted, turned into stercobilin. I spelled that wrong, sorry. It'll be turned into stercobilin and then be excreted, and that's what we call feces. And then whenever it does go to the blood, it's going to be urobilinogen, and then it loses its sugars, and it'll make its way either back to the liver, or it's going to make its way to the kidney and be turned into urobilin, and that's going to be excreted as urine. All right, next it says describe the three mechanisms that contribute to hemostasis. So hemostasis is going to be contributed to by vascular spasm, platelet plug, and coagulation cascade. So with this being said, let's go ahead and dive into how this is going to work. So we have platelets here in our blood, and these platelets are going, whenever an area is damaged, our platelets are going to be attracted to the endothelial cells, because there's a VWF factor right here, which is Van Willebrand factor, and it is going to attach to the platelets because they will have a receptor for VWF, and that will then attach it to the endothelial cells over here. Whenever it does, it's going to allow the flow of the blood will then push it, allowing it to be activated. So the VWF is the thing that is causing it to be activated. And whenever it's activated, it's going to release these different granules, such as ADP and calcium, along with in the dense granules and in the alpha granules, it's going to be releasing more WF, more factor 8, and PDGF. And the factor 8 is going to release histamine and serotonin. And so with this being said, is whenever it does, the ADP will be able to work with the receptors on the platelets as they have that. And then the TXA2 is released by endothelial cells, which both of those combined are going to activate this cell, and it's going to connect it to the platelet, creating this little plug here. And then with that being said, another thing that's happening around the same time is the coagulation cascade. So we're going to have the Higman 7 factor, and it is going to be activated by the endothelial cells, the negative charge on the endothelial cells, turned into activated 7, and then 11 is then going to be activated by the activated 12. Sorry, that's not 7, that's 12. My bad. Oh, something sounded off. Because this is the intrinsic pathway. And whenever that gets activated, it's going to activate 11. Whenever 11 is activated, it's going to combine with factor 8, and it is going to activate number 10, and 10 is going to combine with the cofactor 5, and it is going to activate 2, which is prothrombin, also known as thrombin, and then it's going to activate fibrinogen, also known as factor 1, and then and then factor 1 can combine with the cofactor 13. And so over here from your Higman 12 to your inactivated 10, that is going to be your intrinsic pathway, meaning that is unique. And then from your 10 activated to your 1 activated and 13, that's going to be a common pathway because both extrinsic and intrinsic pathway uses these. And so with the extrinsic pathway, you're going to have factor 7 that is going to react with the tissue factor 3 and be activated. And then 10 is going to be activated by 7, activating 10. It's going to work with cofactor 5, going through the common pathway again. The reason why this is called extrinsic is because the factor 3 is out of the blood and it comes up to the endothelial cells, while the negative charges, the factors react to the negative charges from the inside of the cell. And you need both of them to properly clot. And you do have things that are being given off to as anticoagulant, making sure that you're not just going to start creating clots in your body. And each event is going to cascade, making hundreds and hundreds of more at the time. So by the time you get down the cascade, you have thousands on thousands of the factor that's lower down in the cascade. Alrighty, so we talked about the 3 mechanisms that contribute to hemostasis. We talked about platelets and the coagulation cascade. And we described the extrinsic, intrinsic, and common pathways. Now let's go ahead and talk about TPA, plasminogen, and plasmin. So with these here, you're going to have your, something I forgot to mention is whenever the fibrin is made, it is then going to create like this little net. Create like this little net. catching everything in here and making sure that nothing is coming apart. Alrighty, so you have this little net, you have the platelet plug here, and then you have the net all around it. And so whenever the, sorry, this should be endothelial. Sorry about that. Endothelial cells combined with the fibrin, they're going to activate the TPA. Whenever TPA is activated, it's going to turn plasminogen into plasmin, which that plasmin is then going to break apart fibrin. So that little net is going to dissipate and be no longer moving over here. So you're just going to have broken apart fibrin and your platelet plug. Your platelet plug will be broken apart by something else, but that is not going to be covered in this video. And then your plasmin will also break apart the fibrin in a negative feedback, allowing to make sure that the plasmin does not just go throughout the body, breaking up the fibrin everywhere. And so the plasmin will no longer be made after this because it's going to inactivate the fibrin, so TPA will not be active anymore, and then plasmin will not be active anymore. So that was our quick little video. Hope you liked it. Hope it was a little helpful. I hope you join me for next time.